My name is Zohair Nasser, and today, are you guys joining me?
I'm Kyle Gisselman.
And I'm Stephanie Martel.
And we are presenting on behalf of the Jurassic Cooling team. Today, I'll walk you through some introduction, including targeted customers, design requirement, basic operation of our design, mechanical and electrical system process and updates, budget, and then I'll summarize everything up. And then I'll be more than happy to answer any questions at the end of my presentation. So our targeted customer is, our design is more like designed for campuses and big sporting events. So when it's like, when it's like really crowded outside and really hot, you can just take the Jurassic cooling out and just cool a can and just use it. And then it's really easy to use and set up, so you don't want to use something very complicated when it's like very crowded and hot. And it's ready for the general public as well. So our design requirement, our design should accept a variety of all kind of cans, so that's why we've used a really big cooling chamber, so you could put any type of cans in there. So whether it's like a small can or like a big. So our locking mechanism should prevent the user from getting an access to the inside of our cooling system while the system is running. And then we should use a standard 12 volts battery, which we've already met. And then our system should shut off at 11 volts, which we couldn't verify that, and because the threshold wasn't at exactly 11 volts. And then the other design requirements, we were required to have the system working in between 11 and 14.5 volts, which we've already verified that, so you could use like any sort of battery or any size of battery you want. So the cooler should not exceed 24 inch by 24 inch wide and 12 inch height. And then system should operate in between 30 and 120 F temperature, which we couldn't really verify that. And then one important requirement was to cool the can from 80 degrees Fahrenheit to 39 in under 5 minutes. We could not verify that. However, we could get our can to about 68, and then where you would push a button to start the cooling system, and then choose a desired temperature, and then when the desired temperature is equal to the current temperature, the system will shut off automatically and it'll roar. And then now I'm gonna hand this over to Steph and talk about the mechanical system.
Thank you. So I'll be talking about the overview of the mechanical system and all that encompassed it. So I'll start off with a basic schematic of how we decided to work our cooling system and how it all decided to work together. I'll talk about the Peltier plates, a refresher on what it is, just because it encompassed our entire design and how we are going to cool the can. The construction of the housing, the cooling chamber and all the components in it, and all the different steps we did to get our final design. The cooling system itself, talk about printing the electrical housing, and then all the design challenges we faced when testing our design. A simple schematic. So as you can see, we have water that we decided to use as the coolant, and it gets pumped through the tubes, and we have the 3 rows of Peltiers, and the water goes through the 3 rows of Peltiers underneath and extracts the heat from the bottom of the Peltiers. And then that water goes back through the radiator and expels through a fan, and then that water gets recirculated back through into the pump, and it becomes a closed system. So the Peltier plates, we use VTEC thermoelectric coolers, which basically take heat from one side of the plate and make one side cool, basically. It can operate from negative 22 degrees Fahrenheit to 181, so it's a big difference of cold to hot. And they're pretty small. They're approximately 1.5 by 1.5 by 0.15. For the body of the cooler, we decided to use anodized aluminum because it's extremely lightweight, durable, and cheap, and it's corrosion resistant. We could get enough of it to encompass our entire housing because we wanted it to have a lot of space, so we could put everything in there. For the door and aesthetic, we decided to use a polycarbonate plastic for the actual door where you put your can in. We wanted to implement lights inside of it, but we didn't get the chance to, which was why we had the clear door. But we ended up printing out our logo on the top and putting handles on to make it look a little nicer. For our cooling chamber, we made conduction plates. We wanted it to be the exact radius of a standard can for soda or anything else like that, where it sits in the to maximize surface area. So as you can see, the can is sitting right on the conduction plate, and it's completely, the entire face is around it. For our initial design for the cooling chamber, we just wanted to have 3 columns and have 1 flat and 2 at angles that encompassed 9 Peltier plates with conduction plates on top of them. So we cut out a sheet of metal and just cut plates. And then, as you can see on the left, here's like our final design of this one, where we had the 3, you can't see the Peltiers, but underneath conduction plates, and then having the conduction plates touch the can directly. The sides didn't actually touch like a standard can, so then we decided to use copper, and the copper basically was kind of like malleable, so you could kind of stretch it and put your can in there, and it would encompass more of the surface area. This still didn't work because you kept adding material to increase the surface area, but it take away other materials. So then we came up with our final design. We decided to 3D print a part. So as you can see in the corners, they're the clear sides, and there's one on each side. And there's links that kind of like you can push it and pull it and kind of maximize the surface area. It eliminates extra materials that we needed, like the copper and stuff like that, to where it maximizes the surface area with less material to have heat transfer go through to cool down the can. For our cooling system, we have 3 heat sinks, which the water goes through in parallel, and so then the pump goes through it. The 3 heat sinks were for the 3 columns that we decided to have the Peltiers run on. And then this is inside, so we have a squiggle design almost, is what you would call it, and the water runs through it and maximizes the amount of water in the heat sinks to take away as much heat as possible. For our pump, we used a small brushless pump with a flow rate of about 1 gallon per minute. It ended up not being as strong as we needed it to be, but it had a large lifespan, and it was efficient, and it was inside of the cooling housing. For the radiator, so we had a couple different types for cooling. So we initially started with just 1 cooling block, which is shown on the top right. This was the only thing we had to expel the heat from the heat sink. So we ended up not working as well, and we had some overheating problems. So we upgraded to 220 millimeter fans, and we also added a radiator, which definitely helped. It's still kind of an issue because the Peltier plates get up to 181 degrees, and it's just a small area. So it's still something we're trying to work on. For our electric housing, we 3D printed housing. It wasn't as big as we needed it to be. We had to move the electric housing from the inside of the housing to the outside, so we had to make something for it, but we were extremely constrained by the space that we had because we did have the radiator and the fans and everything outside as well, and it only gave us a small area to run the housing, the wires through. So it was the wire feasibility was extremely difficult because we had to get it through the housing into that and then kind of like go out, and there was a lot of wires, and it was definitely some communication problems with electrical and mechanical teams to get that exactly right. For design challenges, it was definitely hard to maximize contact area. We had 3 different designs and it still doesn't cool a can properly. So we had the conduction plates, the copper, and then we decided on the 3D printed part, which I think definitely is the best option that we have come up with so far. We had a lot of problems with leaking water. We ran a few tests where it did cool a can to about 68 degrees, but water was leaking out of our heat sinks. The silicone, we basically covered in silicone the heat sinks, and it still leaked a little bit, so that's something we have to address or trying to change our design. And then we definitely, as Professor Will mentioned a few OPRs ago, that biology was a concern, and there was definitely hints of biology in our cooling system, and there was a little growth. So we definitely want to spend some more money, if we had any more, on like a water wetter type of thing where algae wouldn't be able to grow. And I'll hand it off to Kyle for the electrical.
Thank you. So I'll be talking about the electrical part of our system today. I'm going to start off going over the custom PCB, move on to the peripherals that we have, and then finish up with some of the Arduino Mega microcontroller. So this is a picture of our custom PCB that we ended up with. As you can see right here, this is the relay. So this is the main power controller of our board. This is what lets our board have 12 volts, so that the Peltiers don't have access to power unless we really want it to. Up at the top, you can see the little green rectangles with screw holes. Those are where the Peltiers actually attach to the PCB. Those are easily tightenable, so we can make sure that we have a firm connection so that we're not going to lose wires anywhere and risk shorting any wires. The bottom row are all signal wires that are going to come from the Arduino. So we have one that's going to go to the Peltier, then some that control the pump and the fans. And then on the far right is actually the power source to the Arduino. So that always has 12, regardless of what the relay is on. So that'd be the one area where our system always has power, so that the Arduino can be functioning and control everything. So here's the circuit, kind of describing what I just said. So as you can see, there's a relay up there, as well as going to the Peltiers, which are all wired in parallel. So they should have similar voltages at the same time. Here's a programming flow chart of how our system works. So once powered on, the system initializes to an off state. That means that there's no power running to anything, and this is declared right at the beginning so we can ensure that nothing happens that we don't want. It then goes into a safety check, so it makes sure that the door is closed and the solenoid is locked so that the user cannot get to anything that we don't want them to unless we allow it. Once that's checked, it'll check if the current temperature has reached the desired temperature, and if it has, it will stop the system. And if it hasn't, it will continue through the loop and check other things, such as the start and stop buttons. So if the start button is pressed and everything else is fine, it'll start the system up. When the system starts, there is a 15-second delay. This allows the cooling loop to engage before the Peltiers are turned on, since they're instantaneously hot, so we need to make sure that we can compensate for that. Similarly, when the system is stopped, we have a 30-second delay that allows the Peltiers to be cooled fully before they heat up the entire interior of the system like we may have experienced. So once the start and stop buttons are checked, it then goes into the up and down buttons, which are the desired temperature value. So if the up button is pressed, it'll raise the desired temperature, and if the down button is pressed, it'll lower it. This is a pretty high-level view. There are a couple other constraints. So it will check if the system is running, so you can't change the desired temperature while the system is running. And then once it has the input from that, it will update the desired temperature and update the display, and then it'll go through the loop again and check safety as the first concern. We want to make sure that we check that as frequently as possible to ensure that no harm comes to the user. This is a diagram of the entire electrical system. So this brown box here is the PCB that I talked about first. I then talked about the Arduino code, which is in the top part of the screen. And then this is just kind of how everything's wired together. So some of the peripherals we used a solenoid that's 12 volts. That's going to be locking the door down, so like once the system starts running, it won't open until I tell it not to. We then have the electronic, or the magnetic switch. So this is just a sensor that when the door is closed, it connects the circuit so we can see that, so the Arduino can see that the door is closed, so we can ensure that the system isn't running in that case. We have a thermistor that we used to monitor the temperature of the can directly. We originally used a DHT22 thermocouple, but we're having issues with contacts. We couldn't get it close enough to the can to actually get an accurate reading. So this allowed us to actually contact it directly and get a more accurate result. Then also was being powered with 120mm fans in the pump for the cooling system. And then we had a TFT touchscreen display that was the output of the system so we could see what was going on. So for future iterations of this project, we would try to professionally print the PCB. We had some issues with soldering since we had to have 2 layers of it, so some need to be soldered to the top layer, some to the bottom. That just increased the complexity and risk for shorting. for the display, the resistive touchscreen ended up giving us some issues with resolution, so we're unable to define zones accurately. So if we could upgrade the budget and have a capacitive display, we think that would help greatly, and then we would eliminate the need for buttons entirely. But it would cost a lot more, so it's something to consider. And then the wiring enclosure ended up being too small. So we measured the Arduino and the peripherals and made sure that those would fit, but we didn't account for the mess of wires we needed to connect everything through. And with that, I'll pass it off to Stephanie to go over the budget.
So I'm going to talk quickly about the budget just because everything revolves around money and we can't really build something without having a budget. So we used in our entire budget, there was really no wiggle room for us to get more of anything we needed. The most expensive item was the metals that we bought. We bought aluminum and copper, which copper can get pretty expensive. So, and then the electrical component, we definitely spent a lot of money on the electrical part because our system is so electrically reliable on having everything work together. And we used Amazon and McMaster-Carr as our main suppliers.
So, in summary, today we've gone over introduction. I've talked to you about our targeted customers, some requirements were met, some of them were not met because the tests were too broad, and then we couldn't get them functional. And then I went over some mechanical system, and that contains some components and design challenges. And then for the electrical system, Kyle walked you through PCB and then some Arduino charts, and then he explained some programming to control our whole system. And then he talked to you about the microcontroller and how it's programmed and coded. And then Stephanie lastly talked about the budget and how are we going to more efficiently use our money, and then eventually get a better project off that. Now I'll be more than happy to answer any questions that you have.
Sadie?
I think it's consider adding a shutdown function, so if someone were to put a can in and it would cool and walk away, it would shut off before it then becomes battery.
Okay, so Sadie's question was, have we considered using a timeout function if someone walks away from it and it just times out on itself? That's more electrical stuff, so I'll kind of answer that.
So in the code, the system is stopped as soon as the current temperature and desired temperature are equal. So at that point, the status is just off. So there's no timeout, because when it's done, it just quits.
So what if it were to reach the desired temperature? They walk away and something broke or something.
So if we did not reach the desired temperature, then at this point we would drain your car battery and you'd be stranded. That's what the future iteration would be destined to fix. Thank you.
Helen?
Why did you use copper to surround the can instead of some other metal that is a better connector for PCB?
So the question was, why do we use copper over certain types of other metals? As a group, we decided that copper would be the most budget friendly and most heat transfer friendly, I guess, to achieve the goal we needed. And we did some calculations on it, and it just seemed like the most plausible thing to do. And we had enough budget where we could purchase a piece of copper and hope that it worked, but it obviously didn't really help much.
Which part of your project is the one most limiting you to reach the target temperature?
So the question was, what part of our project limits us most in reaching the temperature?
I would say it'd be the efficiency of the Peltier coolers. The efficiency is really low on the ones that we got, so just trying to maximize our power usage was a difficulty. So when doing our test with the car battery, after about 6 minutes, we'd start losing power to our Arduino display. And then after that, systems would just start to fall off. So the Peltiers weren't getting the full power that they needed because they're very hungry. So I guess if we could increase the efficiency of those, then that would drastically improve the performance of our system.
What was the problem with these curved metal pieces and then having to repeat them in
So the question was, what was the problem with the conduction plate, the curved ones? So there was no problem with them per se, like the actual conduction plates themselves, but on the sides, when you put a can in, it didn't like curve to the sides of the can basically. And so we wanted to maximize the surface area, and it wasn't maximized that way. It was only like touching the bottom of it with the conduction plates. So then our new design, we have conduction plates on the side too, and then because it's like linked together, it's more malleable, so where you can have more surface area touching it on the sides as well. So it just maximized more surface area for the can that was touched. Any more questions? Thank you.